look at this robot go. But wait, how does it know what to click, where to look, what to grab, and when to move? Meet Magma, a foundation model that doesn't just see the world, it acts in it. Magma is trained to perceive, plan, and execute actions in both digital and physical environments. Its secret sauce, set of mark, and trace of mark. Set of mark helps it spot actionable objects like buttons or handles, while trace of mark tracks movement over time to predict what happens next. By combining these, Magma bridges the gap between understanding and execution, making AI more adaptable than ever. Now let's dive in.
Magma is built to understand and act in both digital and physical spaces. How's that different from previous models? Well, many existing approaches focus on just vision and language. Magma, on the other hand, goes a step further by incorporating action planning and execution. That means it can do everything from navigating user interfaces on a screen to controlling robotic arms in the physical world. Take a look at the visuals here. You'll see how Magma can answer questions about images, like finding objects in a grid or describing unusual items. You'll also see it predicting and executing actions, such as moving objects in a kitchen or performing tasks on a smartphone. Notice how it handles both digital and physical tasks seamlessly? That's the power of its two key techniques: set of mark, which we'll call SOM from now on, and trace of mark, or TOM. SOM identifies actionable objects in images. Think clickable buttons on a screen. TOM tracks how these objects move over time in video, such as the path of a robotic arm. Check out the final set of examples in the figures. They show Magma interacting with user interfaces and real-world environments. What's impressive is how effectively it outperforms specialized models in both UI navigation and robotics, despite training on a smaller dataset. The team has even released the model and code, encouraging more exploration. Curious how they pulled all this off? Let's keep going. A big dream in AI is to create agents that can see, understand, and act in our daily environments. So far, many models only handle specific skills, either vision language tasks or action execution. That's where this research tries something new. Models like Pix2 Act or WebGUM do a fine job navigating UIs, and RT2 or OpenVLA tackle robotics well, but each is stuck in its own domain. Now imagine a single model that can handle both digital and physical tasks. That's the goal. They're using SOM to label interactive objects like buttons on a screen, and TOM to track movements in video. By integrating these techniques, Magma learns from passive vision language data, but also gains action awareness. Look at the comparisons here with other models. Look at Approacher. You'll see Magma outperform them not just on UI tasks, but also in manipulating objects with robotic arms. It generalizes far beyond specialized approaches. It's trained on a mix of open-source datasets, robotics action data, and labeled instructional videos, so it sees a really diverse set of real-world interactions. Ready to see how these ideas developed over time? Let's check that out next. Bringing together vision language understanding and action execution isn't easy. Typically, you'd have separate models for each domain: GPT-4, vision, and Lava for multimodal understanding, Pixel 2 Act and WebGUM for UI navigation, RT2 and OpenVLA for robotics, and so on. Each does its job well, but only in a single environment. Magma breaks this mold. It ingests visual observations and a task description, then produces a sequence of actions. Could be clicks, could be arm movements, or could be just plain answers. To unify all of this, 2D UI actions become text tokens, and robotic movements are discretized positions, allowing a language model to process them consistently. Of course, merging these different action formats is tricky. Translating continuous movements into something a language model can understand takes a lot of alignment work. Wondering how they pull that off? Let's keep going. Now let's talk about the core idea behind bridging digital and physical tasks, this concept of a surrogate task formulation. Because pre-training multiple models for each domain is inefficient, they instead unify everything with SOM and TOM. Here, SOM, or set of mark, labels key parts of an image, like clickable UI elements or relevant points in a robot's workspace. That way, the model learns to act in meaningful regions instead of raw pixels. TOM, trace of mark, builds on that by tracking how these key points move over time in a video, so it doesn't just know where to act, but how actions evolve. Look at Figure 3 to see SOM in action across different scenarios. UI buttons, robot interaction points, and motion cues in human videos are all highlighted. This labeling strategy makes it easier for Magma to learn from a variety of data. Check out Equation 2 too. It formalizes how the model selects actions from a set of relevant locations, boosting efficiency. So with SOM, you have structured action candidates. With TOM, you have temporal dynamics. Together, they let Magma handle tasks in both screens and real-world spaces. Next up, let's see how TOM specifically helps the model learn movement over time. We just covered SOM for labeling static action points. But what if the action involves movement? That's where TOM, trace of mark, really shines. It tracks motion across frames, helping the model understand how actions unfold over time. Crucial for tasks like robotics or dynamic human interactions. Take a look at Figure 4. On the left, you'll notice a robotic arm moving an orange can. Instead of just marking the final spot, TOM shows the entire path. That means the model sees how the arm travels. On the right, you see a person reaching for an object, and again, TOM tracks that future hand movement. It's all about teaching Magma to anticipate how actions progress. Now check out Table 1. It explains when SOM or TOM is applied. In UI navigation, things are pretty static. Buttons don't move. So SOM is enough. But for robotics or instructional videos, you need TOM to follow the motion. Equations 3 and 4 formalize this idea further, making the model autoregressive so it can predict each step based on previous steps. Finally, notice how they assembled their training data. They combined robotics datasets, UI datasets, and instructional videos, like Ego 4D and Epic Kitchen, to teach Magma a broad range of scenarios. This ensures the model can handle both on-screen and real-world tasks. Ready to see how these techniques apply to actual data? Let's keep going. Here's where things get more practical. You might be wondering, how exactly do we label these data sources with SOM and TOM? For UI navigation, it's simpler. Look at Algorithm 1. It uses bounding boxes from the web page or app interface, assigns them labels, and arranges them nicely for the model to learn from. Since buttons typically don't move, SOM alone is enough. But for videos, especially robotics data, it's more complicated. Algorithm 2 uses a motion tracking tool called Co-Tracker to detect meaningful actions in the footage. Remember how camera motion can confuse a model? They tackle that by stabilizing the video first, removing background shifts so it can focus on actual foreground actions. Then they cluster movements to find the relevant trajectories. Figure 5 shows this in action, turning messy motion into clean, structured traces. So combining these labeling strategies allows Magma to recognize static, clickable elements in a UI and dynamic movements in a video. That's a key step toward building a general-purpose agent. Next, let's see the broad range of datasets used to pre-train the model. As you might guess, covering both digital and physical tasks requires a lot of diverse data. Look at Figure 6 to see how the authors categorized everything. They used instructional videos like Epic Kitchens and Ego 4D to capture real human actions. They added in robotics datasets, such as OpenX embodiment, to teach the model about arm trajectories. I navigation datasets like C-Click and VisionU, I contributed examples of clicking and scrolling. And to boost vision language understanding, they threw in resources like Share GPT 4 volts and Lava. Equation 5 steps in to help handle camera motion in video. It calculates a transformation matrix that aligns future frames with the current one, so the model doesn't get tricked by shaky footage. They also used clip-based filtering to weed out irrelevant video clips, focusing on the ones that truly matter for agentic tasks. This rich data cocktail aims to prepare Magma for everything from placing objects in a box to navigating a complex web form. Next, we'll see how all these data sources come together in the pre-training pipeline. Now let's see how Magma is actually trained on all these different datasets. Check out Figure 7. It shows 4 streams of data: natural images, instructional videos, UI navigation examples, and robotic manipulation sequences. They process all of this with a shared vision encoder, then tokenize the text. The final stage is a structured set of tokens that the model uses to generate outputs in text form or as spatial/action steps. Here's a cool part. They run zero-shot evaluations on tasks like UI navigation, ScreenSpot, Visual WebBench, and robotics, simpler few, to see how Magma does without fine-tuning. It beats both generalist models like Lava and specialized models like C-Click or OpenVLA. That strongly suggests SOM and TOM are giving it an edge. An interesting takeaway is that if you just mix UI and robotics data without SOM and TOM, the results aren't nearly as good. Those techniques provide the structured action supervision that truly drives performance. Ready for a deeper look at those ablation studies? Let's continue. So how does Magma really stack up against other models when tested directly? Table 2 gives us the big picture. Magma is tested on a variety of tasks: multimodal understanding, UI action grounding, and robotic manipulation, and it comes out on top in all of them. Models like Lava or OpenVLA do well in their own specialties, but can't match Magma across the board. If you check out Figure 8, you'll see a detailed breakdown of robotic tasks. Magma is compared against OpenX embodiment. Tasks include placing objects in a drawer or stacking blocks. Magma consistently gets higher success rates, particularly in more complex scenarios. Then glance at Table 3 for the ablation studies. If you remove SOM or TOM, the performance drops. Just mixing data from both domains isn't enough. You really need that structured action supervision. Finally, the authors do some efficient fine-tuning on Mind2 Web and AITW. That helps Magma improve even more on UI navigation tasks. Wondering if Magma can adapt further with a little extra training? Table 4 and Table 5 answer that question by focusing on UI tasks. They use Mind2 Web for web interfaces and AITW for mobile apps. Magma outperforms GPT-4V and Mini-GPT across the board. The reason? SOM and TOM help it pinpoint where to click or tap. On the robotics side, look at Figure 9. You'll see a Widow X 250 arm in real-world tests. Magma is asked to pick up objects, place items in containers, and manipulate cloth. It still outperforms OpenVLA, especially on brand new tasks like push cloth left to right. This suggests that its spatial intelligence helps it generalize beyond what it's seen before. All in all, Magma's ability to transfer its knowledge from one domain to another is super promising, and that's going to matter a lot as we push AI into more diverse real-world settings. Now let's talk spatial reasoning and multimodal understanding. These are huge for AI agents. Take a look at Figure 10, which shows Magma's robotic fine-tuning results on the Libero benchmark. Even with only 10 trajectories per task, Magma beats other models in real-world robotics challenges. Clearly, SOM and TOM help it learn how actions unfold in space. Sexual 6 takes us into pure spatial reasoning tasks like VSR, Blink, and spatial eval. Despite training on fewer images than, say, GPT-4, Magma matches or even outperforms them. Figure 11 illustrates an example question, highlighting how Magma provides the correct spatial reasoning answer. Then Table 7 looks at vision language benchmarks such as Text VQA and Chart QA. Again, Magma's performance improves thanks to SOM and TOM. The model gains a better grasp of how objects relate to each other in space and how textual elements connect to visuals. This is a big deal, showing that structured action supervision elevates not just robotics and UI tasks, but also more traditional vision language challenges. Finally, let's see how Magma handles video-based question answering, QA. That's often considered one of the toughest tasks because you need to understand changes over time. Look at Table 8. Magma is tested on Intent QA, Next QA, Video MME, and MV Bench. All these benchmarks demand strong action, object, and spatial reasoning. Magma outperforms nearly every other model, even with fewer video samples in its training set. If you're wondering why it does so well, SOM and TOM are the secret. By incorporating structured action labels, Magma gains a clear sense of how objects move and how actions unfold. The improvement over IGVLM on Next QA, nearly 28%, speaks volumes about the power of anticipating motion and understanding trajectories. The conclusion here is straightforward. Magma is the first foundation model built for multimodal agentic intelligence. It navigates both digital and physical tasks, leveraging SOM and TOM for structured supervision. That said, the authors point out potential issues with social biases. If the training data doesn't represent everyone equally, the model may carry skewed behaviors. Addressing these biases is an important step in making sure Magma is fair and reliable in real-world applications. Thanks for joining us today. Happy learning and stretching together.